So, okay, I'm gonna start recording now. Let's see. So the definition. No, okay, since didn't record, so those who didn't watch live couldn't see the movie. So there's the V1 to VK, and is called an orthogonal basis of subspace W in Rn if one, this set is an orthogonal set, and two is that it's not only orthogonal, but it should also be a basis.
That what does it mean to have a basis? So one, it should be not too small. I just put on my headset so for better sound quality. Is this okay? Can you hear me? Good.
Yes.
Okay. Yes. Yeah. Thanks. So okay. Thanks. So one thing is should be not too small, which means that the span V1 to VK, and this should indeed span the subspace W. And two is should be not too large, which means that this V1 to VK and this set should be linearly independent. Okay, so what I'm going to say, so this is just a simple definition. Give me an orthogonal set and give me a subspace. I check whether it's the basis of W. But I want to say this one. Someone, could you please mute? Hello? Okay, good. So what I want to say is that this is linear independence one is automatically satisfied by orthogonality, which is if you really give me a set of orthogonal vectors, then they must be linearly independent. This is actually a theorem. So V1 to VK is an let's say orthonormal set. Everyone, could you please mute? Let me see whether I can force to mute some of you. Okay, too complicated. Yeah, please mute unless you want to ask a question. Orthonormal set. Then this set is, yeah, if you really have a question, could you speak up? Because it's not that convenient for me to look at the chat. This set. It must be linearly independent. Any question?
Is this only true for orthonormal sets or all orthogonal sets?
So the question is why I say orthonormal instead of orthogonal. This is to get rid of the zero vectors.
Can you go back one slide really quickly?
Here?
Yes. Oh, I just need to write it down. Thank you.
Yeah, okay, no problem. So yeah, I mean, this definitely works for orthogonal set. And I say orthonormal just to make sure that none of them is zero. Any other question? Proof? So to prove this, assume we have a vector equation, C1, V1, ck vk equal to 0 vector. Now what I'm going to do is a very general technique that we're going to do again and again and again in chapter 6, which is to do a dot product on both sides of the equation. So what I'm doing is I pick an arbitrary I, do a dot product, I copy this thing down, equal to, the right hand side is dot 0, which is 0. Okay, why do I want to do this? So obviously, if this line is true, then as a necessary condition, this is true, not the other way around. So the reason is it is already an orthonormal set, which means that let's see that I don't take this for clarity. Let's say not VI. I just say V1. Okay, I just take V1, but any VI would work. Then this is V1. So this is a C1. V1 times V1 is 1 because it's orthonormal. Then the second one is a C2, V1 dot V2, but it's orthogonal. It's 0, 0, equal to 0. So what we have is C1 equal to 0. This is the most important line. Any question? Okay.
Can you walk through the logic of that last?
Okay, let me say again. So it's only 3 lines, but it's important technique. So I want to show they're linearly independent, right? Therefore, what I want to show is C1, if this is true, this vector equation is true, then C1 to CK must all vanish. This is what I want to prove. How do I prove it? I start from V1. I do a V1 dot on the left and right hand side. Left hand side is this, right hand side, because it's dotting with a 0 vector, it is just a 0 scalar. The left hand side can be computed very simply because it's an orthonormal set. It is orthonormal, therefore V1 dot V1 is 1, V1 dot V2 is 0, V1 dot VK is 0. Therefore, I have deduced C1 is 0. Is that clear?
Yes, thanks.
Okay. Any other question? Now I apply to O VI. I just a V2 dot, V3 dot, then I just get C1 equal to CK, and they're all 0, and therefore linear independence. Question? Okay, so now you see that if you already have an orthogonal set, then all you need to check is to see whether it's a basis. All you need to check is whether the span is indeed equal to W. It must be linearly independent. Now let's say why orthogonal basis or orthonormal basis is useful. So let's say that I start from a basis. I call it B1, the Bn. And this is a basis of Rn. And now you give me any vector V that is in Rn. I want to find the B coordinate. How do I find that? I solve a linear system. So in chapter 4, what we do is that since they are all in Rn, form a linear system. You want to be N, and therefore this is V. And this, the solution gives me VB. Any question? Okay, so you all remember that. Now let's say that now if B is an orthogonal set, since I said this basis is an orthogonal basis. Now how do I find VB? So recall that, so let me just use a vector C to denote this VB so that I don't have too many brackets. Okay, C literally means this coordinate. So this is given by it's a component C1 to Cn. Then we have the vector equation V equal to C1 B1 Cn Bn. How do I find C? As I said before, you solve a linear system and get the C. Now I use the same trick again. I use B1 dot V equal to B1 dot on both sides, C1 B1 dot, Cn Bn dot. So the left-hand side is, it is what it is. The right-hand side, I can actually simplify it a little bit. C1 here, B1 dot B1. I didn't say it is orthonormal, so I keep the square of the length here. And then I have C2 B1 dot B2, but it's an orthogonal basis set, so B1 dot B2 is 0. So that all the way to the last one, B1 dot Bn is 0. So this is C1 B1 dot B1. So I can apply the same technique to all the to all components. Therefore, I have a Ci for any I. I have a Ci for any I. This is equal to so this is equal to Bi dot V divided by Bi dot Bi. And these are two numbers. And this is I from 1 to n. This is really simple to compute. Why? Because there's a no linear system to solve. And the computation is just only two inner products. And you have seen that inner product or dot products are really easy to compute. You just element-wise multiply them and add them together, then you're done. Furthermore, if B is a orthonormal basis, then even the denominator, it is gone. We have a Ci equals to Bi dot V. Any question? Let's look at the example.
Professor, could you go back up a little bit, just
Yeah.
so that?
Okay, example.
Thank you.
Okay. We still, let's see, B1, B2, B3. And we took exactly the same three vectors as in the warm-up here, these three, but maybe it's easier for me to just copy it because we have so we're several pages apart. Now I just rename them to be 1, 2, 1. B3 is -2, -1, -2, 5. So now we want to find VB. So, I mean, we can really, as an exercise, find VB in the old way by solving B1, B2, B3, V. So this will leave to you as an exercise. Now we want to do it in the new way, which means that we have checked in the warm-up that B is an orthogonal set. And furthermore, B is a orthogonal basis of R3. Why? Because there are 3 vectors and they're linearly independent, so the span must be R3. Then I can just evaluate, I can just, oh, sorry, I didn't write what V is. So V, let's say it's a 1, 0, 1, okay? Give you some vector. So now I just evaluate the 3 coordinates. The first coordinate is B. I just literally follow that. So this is B1 dot V divided by B1 dot B1. B1 dot V. So this is 2, 1, 0, 0. So this is 2. And B1 dot B1, it is 5. Any question? Okay. C2, exactly the same procedure. B2 dot B2. So B2 dot V, so this one is 1, 0, 1. So this is 2. B2 dot B2 is 1, 4, 1, 6, 1 over 3. C3 is B3 dot V, and this is B3 dot B3. So this is B3 dot V is -1, and this is 5 times 1, this is 4. And divided by 1 plus 4 plus 25, this is 30. And therefore, this is 2 over 15. So you see, this is way easier than solving the linear system. Any question? Okay, now let's talk about a concept that is very much related to the orthogonal basis set, and it is called projection. So what is a projection? Okay, so I mean, we have all seen in the daily life. So the idea of a projection is, let's say that, so this is sun. Okay, this is the ground. And this is, let's say, this is me. How should I? Maybe like this. Okay, this is me lying on an imaginary chair. So the sun is right above me. So the sunlight is just goes orthogonal to the ground. What does it mean is that, so so the sunlight is orthogonal to the ground. So what is the projection? It is the shadow of me on the ground. So, which is this thing. And this is my projection on the ground. So what does this mean in a more abstract sense? It means that if I just simplify this, remove the useless me, and just think about a 2-dimensional thing, I want to project a vector V onto the x1 axis. So, so this one, let's call it U, is the so-called projection of V onto the x-axis. And it is the defining feature is that the difference between v and u. So this vector is v minus u is orthogonal to u. Any question? Okay, so let's do some more explicit computation. So it's really simple, right? So more explicitly, so let's say the vector is v1 and v2. I want to project this to the x1, and therefore I know that u, this vector, is v1, take the first component, times e1. So it is this is v1, 0. Now, v minus u, that's called the z, go to v minus u, and this is 0, v2. Obviously, now you find the projection u and the difference z is 0. So, which means u is orthogonal to z. So this is a very simple example, just like at the beginning of chapter 6, when we defined inner product, we considered the inner product between u and v, and the u is along the x-axis. Later, we realized that there must be an algebraic construction so that it doesn't really matter whether u is along the x-axis or not. How do I generalize this to a more algebraic setting? Let us again take a look at an example. So let's say u is 0, 1, 2. V is 1, 1, 1. Now the goal is to find, the problem is to find a number, alpha, which is a real number, such that v is alpha u plus z. And u dot z is 0. So I asked you to find alpha, but I didn't tell you what the z is, so you essentially also have to find z. And if you compare this example, we haven't said how to solve this, but you can see this must be a generalization of the previous one. We went from R2 to R3. U plays the role of x1, but this is no longer a special vector. It's just some arbitrary vector. Alpha plays the role of this coefficient here, v1, and z plays the role, which is the difference between v and alpha u. Any question? Everyone understand what the goal is? Very good. So the technique we're going to use is exactly the same technique we have used before, which is to do a dot product on the left and right hand side. As I said, this is a really useful technique. So on the left hand side, I consider u dot v. On the right hand side, I have alpha u plus c. As I said before, we don't know z, what z is at this point, but it doesn't matter. Why it doesn't matter? Because u dot z, as I said, must be 0. And I do know what u, v, u is. So this one gives me alpha as a number is equal to u dot v divided by u dot u. And now I can directly compute it. So u dot v is 1 plus 2, so it's 3. U dot u is 5. So I directly found that alpha is 3 over 5. So just for fun, we can compute what z is. So z is v minus alpha u. And so alpha is 3 over 5. So this is v is 1 minus, so this is 1. And 1 minus that is 2 over 5. and 1 minus this is minus 1 over 5. Okay, so we found Z. Now, if you want to check whether U and Z, these two vectors are indeed orthogonal, you can do a direct computation. 0 times 0 is 0, 0 times 1 is 0, 1 times 2 is 2, 2 times minus 1 is minus 2, so it is indeed orthogonal. Any question? Good. Now let's get rid of the concrete numbers and talk about the general setting. You give me a vector v. What did we do? So you give me a vector v, okay? And let's say this is in Rn. You give me a non-zero vector u that is in Rn. Then I can always decompose it. So I'm drawing R2 here, but it really now means Rn. So I have a v here, and I have a u here. I can now consider the span of u. Let's call it w. What is the span of u here? This is just a line. As I said, it doesn't really matter whether this is R2 or higher dimension. By now, you should be quite familiar with this. It is just the collection of all the vectors that can be given by C times U, where C is a real number. So I consider that. I can consider the projection of V onto U. And what does it mean? It means that I should be able to find a Z so that V is equal to some number plus a Z, and it satisfies Z dot U is 0. So what it means on this picture is that I don't know what is alpha. I mean, alpha times U is here, but I know that I want to choose alpha to be not too large, not too small, to be exactly here, so that the difference between V and alpha times U is a vector Z, and Z is orthogonal to U. And this line here is called the projection. It's called projection. So by doing exactly the same computation as we did before, you'll find that this one is just a u dot v, u dot u. As we said, u is not a zero vector, so this is guaranteed. The denominator is guaranteed to be non-zero. So as I said, this one is the projection. So let me define it more formally. Projection of v onto w, this is how it reads, is u dot v divided by u dot u. This is a number, u. It is some constant times u, and therefore this is in w. It's called the projection. So what this line reads, I can also write it to be v equal to projection of v onto w plus a z that is orthogonal to the subspace. Any question? So there's no particular reason why w has to be a one-dimensional either. I can consider w to be a k-dimensional subspace, span w1, wk, and this is a, let's say, orthogonal basis set. Orthogonal basis set, not the span, but this is a set of vectors, orthogonal basis set, and therefore this is a k-dimensional subspace of Rn. Let's consider k equal to 2, because the largest I can draw is R3. So So this is W, so that has two bases. So this is the origin. Let's say this is W1, some orthogonal stuff, W2. Okay, so this defines a plane. Now I have a vector called V. So how do I compute the projection? Intuitively, I can just do this. So this one is the projection. This is called the projection of V onto the subspace W. It's important. It's you always project onto a subspace. And the difference is, so this is a Z equal to V minus the projection. And Z should be orthogonal to W1, and Z should be orthogonal to W2, and therefore Z is actually orthogonal to all the vectors in W. Any question? Good.
Professor, can you
Yeah.
go over the logic of that part again? Why Z is orthogonal to all vectors on W?
Okay. So the part is what is, so let me repeat the question. The question is why Z is orthogonal to W1, Z is orthogonal to W2, then Z is orthogonal to all the vectors in W. Is that right?
Yes.
Okay, yeah. First of all, let me clarify here is K equal to 2. So only W is span of a W1 to W2. So now let's say, this is a good question. Take any vector W in the subspace W, then I can always write it using the basis to be W1 plus C2 W2 for some C1 and C2 in R. Now you see D times W equals to Z1 D times W1, C2 Z dot W2. I have already known that Z is orthogonal to the two bases, and therefore this is 0, this is 0, so this is 0. So Z is orthogonal to all the W in that subspace. Is that clear?
Thank you.
Okay. So finally, let us maybe do an example. So W1 is 1, 1, 0. W2 is 1, 1, 1. And V is 2, 1, 1. And so here I defined W to be the span of W1 and the W2. The question is whether you can compute the projection of V to the subspace W. Okay, so now you see that I just give you a procedure, right? Maybe you say, okay, that's easy. No, I did, sorry, I missed a step. Let me get back. So what is this projection of W? So this projection of W, V to W, is given by completely analogous to before W1 dot W1 V dot WK WK dot WK WK. And then is you can check Z defined in this way, which is a Z equal to V minus the projection, is indeed is indeed orthogonal to W1, WK, to each of those as an exercise. Okay. So this is the projection. Now I asked you to compute this. You say this is easy. Let me just compute v.w1, v.w2, and do the computation. And you check z, and I will leave to you as an exercise and find that this doesn't work. And z is actually not orthogonal to w1 or w2. Said, wait a minute, what's the problem? The problem is that this relies on that w, what was the assumption? Is an orthogonal basis set. So the first step you, when you want to apply this, is to check first whether the basis set, I mean, the subspace is always well defined, but the basis set can be arbitrary, is an orthogonal basis set. Now I have two vectors, so it is really easy to do. So W1, W2. So this one is 1 plus 1 equal to 2. This is not equal to 0. So, I mean, I cannot really use the formula before. I say, okay, I got stuck. But it's not really. I mean, our first job to use this formula then is simply to say, well, I want to construct an orthogonal basis set. Then I can apply this formula to compute projection V to W. So construct an orthogonal basis first. How do I do that? Now you see, previously that's a Z, seems to be a garbage, right? I mean, it's orthogonal to W1, but it is actually very, very useful because I can decompose W2 to be the projection of W2 onto the span of W1. Too tight. So on projection of W2 onto the span of W1 plus a Z, let's call it W2 tilde. So this W2 tilde satisfies, it is orthogonal to W1, and therefore W1, W2 tilde is an orthogonal basis that we want. So add a page. So we literally do this. How do we do that? So W2 tilde is W2 minus W2 dot W1, W1 dot W1, W1. I'll skip the computation. And you can check after the class, this is 001. And now you can now apply the formula. And give to you as an exercise the projection of V to W. So this is using the new orthogonal basis. And this is 3 over 2, 3 over 2, 1. And what it does is V dot W1 divided by W1 dot W1 times W1 plus V dot W2 tilde, that's important, and divided by W2 tilde times W2 tilde, it's quite a mouthful. and you just add them together, you'll get this projection. Now you compute V minus this projection. That Z will indeed be orthogonal to W1 and W2. Okay, let's stop here. I hope you stay safe and healthy and have a nice spring break. And we'll meet again after the spring break.